Welcome to lecture 7 on circles. So, in the last lecture we had finished the derivation of the equation of the direct common tangents to two given circles for the first case where the circles were not intersecting each other, neither were they touching each other. For the same case, we will now resume with deriving the equation of the transverse common tangents to two given circles. So, let these be the two given circles with centers C1 and C2. So, C1 is the center of the first circle having coordinates x1, y1. C2 is the center of the second circle with coordinates x2, y2, and let C1, C2 be the line joining the two centers. If we recollect, the transverse common tangent is a tangent which is common to both the circles, but it is such that the circles lie on the opposite sides of the tangent. So, this is one of the transverse common tangents, because if you look at the tangent, then this circle lies on this side of the tangent and the other circle lies on the other side of the tangent. And let us say that this is the point P, which is the point of intersection of the straight line joining the two centers with the transverse common tangent, and let this point P have coordinates gamma and delta. Let this point be A, and we will say that this point here is point B, and let us join C1 to A and C2 to B. Then clearly this angle and this angle are 90 degrees, and then as before it is quite clear that this angle and this angle are equal. So, let us see the two triangles PAC1 and the other triangle is PBC2. And what we will see is that the two triangles are similar to each other, because all the three angles of these two triangles are the same, because first of all one of the angles is 90 degree, and this angle and this angle are also equal, and therefore, the third angle has to be equal, this and this will also be equal. So, given that these two triangles are similar, we can now write down the similarity ratios for these two triangles. Now, this distance is R1 and this distance C2B is R2. So, from the similarity ratios, what we get is that PC1 divided by PC2, PC1 divided by PC2 has to be equal to R1 divided by R2. And if we work it out, so given this fact, what it means basically is that the point of intersection of the common tangent with the line joining the centers of the two circles. So, this point of intersection divides the line joining the two centers in the ratio of the radius of the circles. So, that is what this equation tells us, and this division is internal, unlike in the case of the direct common tangent, where the point of intersection was dividing this straight line joining the centers externally in the ratio of the radii. So, here the division is internal. Now, starting from here, it is very easy, just like what we did earlier, to find the coordinates of this point of intersection here. So, and that is left as an exercise for the students So, one can show that the x coordinate gamma of the point P is given by r1 x2 plus r2 x1 divided by r1 plus r2, and the y coordinate is given by r1 y2 plus r2 y1 divided by r1 plus r2. Now, given this value of the coordinate of this point of intersection of the transverse common tangent with the line joining the centers of the two circles, we can write the equation of the transverse common tangent. So, let us say that the slope of this transverse common tangent is m, and we know that it passes through this point P with coordinates gamma and delta and therefore, we can say that for any point x y, comma y on this transverse common tangent, the coordinates x and y of any point on the transverse common tangent has to satisfy this equation, which is y minus delta is equal to m times x minus gamma. So, this is the straight line equation for this transverse common tangent. But then although we know we have been able to express delta and gamma in terms of the radius of the circles and the coordinates of the centers of the two circles, but the value of m is still unknown, and that is what has to be found out. So, just like what we did in the previous lecture, what we observe from here is that the slope m has to be such that the minimum distance of this transverse common tangent, which is this line here. So, the minimum distance of this straight line from the center C1 of the first circle must be r1, and similarly the minimum distance of the same straight line from the center C2 of the second circle must be r2, and a little bit of calculation will show that both these things are one and the same. So, we will again get two equations. So, again if we go back to one of the slides in the previous lecture, we have derived the formula for the minimum distance of a given point x naught y naught from a given straight line. So, this straight line is having slope m and it passes through a given point alpha beta. Then in that case the squared distance, the squared minimum distance of this point from this straight line is given by this expression. So, we will again use that expression. So, the only thing is that in our case the point from where we have to find the minimum distance is the center of the first circle, and the straight line to which we have to find the minimum distance to, the straight line is actually the transverse common tangent, which is known to pass through this point P having coordinates gamma comma delta, and this transverse common tangent has a slope m, and therefore, this minimum distance, which must be r1, because otherwise this line will not be the transverse common tangent to the first circle. And therefore, from the slide in the previous lecture, the right hand side here gives us the squared minimum distance. So, we just have to replace x naught and y naught with x1 and y1 and alpha and beta with gamma and delta. So, what we get is the squared distance is m into x1 minus gamma minus m times x1 minus gamma minus y1 minus delta square upon 1 plus m square equals r1 square. And then similarly we get a similar equation for the second circle also, But then just as we had shown, just as we had shown in the previous lecture, even for this case we can show that the other equation is nothing but the same as this equation. So, the other equation that we will be getting is for the second circle, which is this equation, this equal to R2 square, but then it can be shown that these two are nothing but one and the same, and therefore, we will proceed only with one of the equations, and when we solve this equation we will again get a quadratic equation, an equation which is quadratic in M, which means that there will be two roots real, both will be real valued roots, and therefore, we will get two different equations for the transverse common tangent. So, if we so that is what we had gotten in the previous lecture also. So, the roots, let M1 comma M2 be the two roots of, let me say this equation to be 3 of the quadratic equation resulting from equation 3, and then the equation of the true transverse common tangents is, so the two equations will be, one will be y minus delta is equal to m1 times x minus gamma, and the other equation will be y minus delta is equal to m2 times x minus gamma. And also interestingly, so let me draw the second transverse common tangent here. So, the second transverse common tangent will also pass through P, and that is clear because if let this be the first, if we see here the point P, which is gamma comma delta, will, it can be seen that it lies on this straight line as well as this straight line, and therefore, the point P lies on both the tangents. So, the next case is when the two circles touch each other externally, say, so they do not intersect, but they touch each other at one point. So, let us remember what had happened in the previous case. In the previous case, the circles were neither touching nor intersecting, and then we had two direct common tangents and two transverse tangents as well. This was the point of intersection of the transverse common tangents with the line joining the centers of the circle. Now, what if we start moving this circle towards the first circle along the same this line joining the centers? Then it is expected that, for example, if this smaller circle with center C2, if the center C2 moves to, let us say, this point here. So, then we have the circle C2, the second circle to be like this, and let us say that this is the new point C2 prime. So, in that case we will see that the transverse common tangents become like this, and then this is the point of intersection, which is still on the line joining, will still lie on the line joining the centers of the circle. But we start seeing that the two transverse common tangents the angle between them, which is this angle. So, earlier we had this angle and now the angle has reduced, and as we move further, let us say, then what we expect is the moment this smaller circle touches the first circle, we expect that these two tangents will probably become the same one, they will become one single transverse common tangent. So, to see that, one could actually go back, if we go back to the first case, and especially when we were deriving the equation of the two transverse common tangents, we had this particular quadratic equation, and we said that there will be two roots m1 and m2 for the slope. But then what we can see is that from here, if, as we will derive it now, that as when the second circle touches the first circle, in that case we will have two equal roots here. So, this quadratic equation is going to have two equal roots, which means that there will only be one transverse common tangent. So, to see that, so obviously when if we recollect the coordinates of the point P was gamma comma delta, where gamma and delta were given by these two equations, and if we open up this particular quadratic equation, a little bit of simplification gives us this quadratic equation. So, what we get is m square into r1 square minus x1 minus gamma whole square plus 2m into x1 minus gamma into y1 minus delta plus r1 square minus y1 minus delta whole square, this equal to 0. So, this is the quadratic equation that we will get from here. We just have to take this here and then just do a shuffling of the terms, and this is what we get. So, this point P so now when this let us see the condition under which this quadratic equation is going to have equal roots. So, it will have equal roots if and only if the discriminant is 0, and the discriminant is 4 into x1 minus gamma whole square into y1 minus delta whole square minus 4 times r1 square minus x1 minus gamma whole square times r1 square minus y1 minus delta whole square, and we need this to be 0. So, if the coordinates gamma and delta of the point of intersection of the tangents, transverse common tangents, satisfies this equation, only then will it happen that we will have only one transverse common tangent. But if we simplify this further, because the radius of the first circle is not 0, what we will get is that we will get r1 square. So, this condition is the same as the condition that r1 square is x1 minus gamma whole square plus y1 minus delta whole square. But what this is telling is that, and if you remember, this distance is nothing but the distance between the point. So, this was the point P. So, this is the point P over here. So, this distance is nothing but the distance between P and the center C1. So, square of that. So, P C1 square. So, essentially what this implies is that we will only have one transverse common tangent only if and only if PC1 is R1, which means that the distance between the point of intersection of these two well, now that we only have one tangent in this case, when when we have only one common tangent, the point of intersection of that tangent with the line joining the two circles, that point is such that the distance of that point from the center of the first circle is R1. What this basically means is that this point is actually on the first circle, it is on the circumference of the first circle. So essentially what we have shown is that we will have only one transverse common tangent only in the case where the point of intersection of that common tangent with the point of intersection of that particular common tangent with the straight line joining the centers of the two circles. So, that point of intersection P is lying exactly on the circumference of the circle. So, PC1 is equal to R1, and this is the transverse common tangent. So, there is only one transverse common tangent when we have only one root, or basically both the roots are equal. So, under that situation we have only one transverse common tangent, and in that case we saw that the point of intersection of this single transverse common tangent with the line joining the center. So, that particular point of intersection P will lie on the circumference of the circle. Now, since this is a common tangent, to both the circles, it means that this line is also a tangent to the second circle, and further we know that this point P lies on the straight line joining the two centers. So, if we just produce this line further, which means that this angle is also 90 degrees, the center of the second circle has to be somewhere on this line. So, we know that the center of the second circle has to lie on this line which we have produced, which basically we have joined C1 with P and we have extended it further, and the second circle also must have its center on this line. Plus we know that this same straight line here, which is a tangent to the first circle, is also a tangent to the second circle. So, therefore, the shortest or the minimum distance of this straight line from the center of the second circle must be the perpendicular from the center of the second circle to the straight line, but the perpendicular is just this line, this part of the line segment, which also passes through P, and therefore, it is clear that P is the point P basically must also lie on the circumference of the second circle. So, we have a situation like this. And now, we know precisely that this point P lies on both the circles, and it also lies on the transverse common tangent, right, and therefore, it is clear that both these circles are, now because this point is lying on both the circles, it is clear that this point is common to both the circles, and therefore, both the circles are actually touching at only this point, and they are not touching, they are not intersecting, because if they had, if there was an intersection something like this. So, if we have this situation, then there is no, we can't have any transverse common tangent. So, this situation will basically happen when the quadratic equation that we have here has no real roots. So, the first case was when it had two real roots. So, when it had two real roots, it was the first case where the two circles were neither touching nor intersecting. The second scenario is what we were doing just now, where this quadratic equation just has a single root. So, when that happens, both these two circles will be exactly touching each other at a single point, and they will just have one transverse common tangent. Then further, if this circle center of the circle C2 moves towards C1, which could be this case, in this case what will happen is that this particular quadratic equation will have no real solutions for M, and that is why there will be no transverse common tangent in this case. Also, now in this case, which is the second case where there is one transverse common tangent, it is very easy to find the equation of this particular tangent. So, that will be, so we just have to again, so basically we won't have two tangents, we will just have one tangent, and the equation will be of this single transverse common tangent will be y minus delta is equal to m into x minus gamma, where m is the value of the equal roots of that quadratic equation in M. So, there is only this single transverse common tangent. And of course, how do we suppose if we are given two circles, let us say, and if we are only given the equation of those two circles. So, we are only given the equation of two circles, and then we are asked to find out whether is it condition 1 that is happening or is it condition 2 that is happening. So, for condition 1 we had said that we will find the distance between the two circles between the center of the. So, this was condition 1 here. So, this is case 2 and this was case 1 where the two circles were neither touching nor intersecting each other, and for this case 1. So, for case 1 we had said that if we are given the equation of the two circles. So, from the equation we can find the coordinates of the center, we can also find the value of the radius of the two circles from the general equation of these two circles. And then what we can do is we can find the distance between the two centers, and if the distance between the two centers happens to be strictly greater than the sum of the radii or the sum of the radius of the two circles, if this happens, then it is clear that the two circles are neither touching nor intersecting each other. But if it so happens that the distance between the two circles, which in case 2 is exactly equal to R1 plus R2, and I mean given the two equations of circles, we can easily find the coordinates of the center, and therefore, we can easily find this distance. So, we can find this left hand side, and of course, from the equation of the circles we know their radius, we can add the radius, and if these two are exactly equal, then we know that we are in case 2 where we have only one transverse common tangent. But of course, in case 2 we will still have two direct common tangents, and finding the equation of the direct common tangents will be the same as that in case 1. So, now we can take the third case, which we have already discussed a little bit. So, this third case is where the circles happen to intersect each other. So, if the circles intersect each other, so firstly, how do we find out that they are actually intersecting each other? So, we will again, given the two equations of these two circles, we will find the distance C1 C2, the distance between the two centers, and we will also find the radius of the circles. So, if C1 C2 is less than R1 plus R2, then it is clear that it is neither case 1 nor case 2. But then we could have two possibilities if this happens. If this happens, this is one possibility. The other possibility could be something like this. So, C1 is here, C2 is there. So, this is the smaller circle and this is the bigger circle. The bigger circle has center C1, the smaller circle has center C2. or we could even have this kind of a situation where the smaller circle is touching the bigger circle from internally from inside. So, how do we distinguish this case from these other cases? What we can say is that if the distance between the circles is greater than modulus of r 1 minus r 2, then it has to be this case. Because what will happen is that, so the how do we have got to this third case by just basically moving this smaller circle along this line. So, earlier the smaller circle was somewhere here. So, this was case 1 where they were neither intersecting nor touching. Then the smaller circle came and over somewhere over here, and at this. So, this was case 2, this was case 1. So, in case 2 it was exactly touching the bigger circle at just one point, and then if we move this circle from here to here and then if further ahead, then of course, we are in case 3 where they are intersecting, and then if we even move it further we will arrive at this case. So, even if we even move it further, then we will actually arrive at this case where the smaller circle is something like this. So, in this case the smaller circle is actually touching the bigger circle in blue from inside. So, it is touching it internally, but in this case if we see, this is R 1, this is R 2. So, this is basically this case. So, if we take this case, this is R 1 and this is R 2, or if we can draw it separately. So, this is a smaller circle, center C 1, C 2. So, this is R 1 and this is R 2. So, therefore, the distance between these two centers is R 1 minus R 2, and we just take a modulus because of course, here we are assuming R 1 to be larger than R 2, but it could be the other way around. So, that is why we have to take modulus. So, if the smaller circle comes keeps on coming closer, if the center C 2 keeps on coming closer till this case happens. So, as long as the distance, so when this case happens, we have C 1 C 2 equal to mod of R 1 minus R 2. If the distance C 1 C 2 is greater than this, if it is greater than this value, then it is clear that the circle is not touching internally. The smaller circle is something like this. So, this is the case that we have now, where this circle. So, in this case where the distance between the two centers is first of all less than R 1 plus R 2, but it is greater than the absolute difference between R 1 and R 2. So, in that case what we will have is that the two circles will be intersecting with each other. So, it will be something like this. So, they will be intersecting at exactly 2 points, and of course, for this case then what will happen is that there will be no transverse common tangents, because what will happen is that both the roots will become non-real, but we will still have two direct common tangents whose equation can be found again using the methods used in case 1. And then of course, we have the case where the two circles are going to touch each other internally. So, if we move the center of the smaller circle even closer to C1, then so in the previous case so earlier we had this case 2 where the center of the smaller circle was such that the distance between the centers was r1 plus r2, and then we moved this circle a little closer along the same line joining the centers. So, the center came to this point and the circle was then something like this, the smaller circle was something like this, and this became the center. So, this is the case, this is case 3. In this case we have already seen that they are intersecting at the two circles intersect at two distinct points. And then if we further move this circle, the center of this circle C2 towards C1 along the same line in such a manner that they touch, the second circle touches the first circle internally. So, what we mean by that is the second circle basically has center C2 in such a way. So, this is center C2 in such a way that this red circle, smaller circle and the bigger blue circle touch exactly at this point. So, this point is P, and of course, this will happen only when C1 C2 is equal to the absolute difference between R1 and R2, because this is R1 and this is R2. As the center of the smaller circle comes closer and closer to the center of the first circle till this condition is satisfied. So, the moment this condition is satisfied, we can clearly see that the second circle touches the first bigger circle internally at this single point of contact P, and in that case there is one common tangent, there is only one common tangent, and this is a direct common tangent. So, in this case there will be no transverse common tangents, there will be just one, there will be only a unique direct common tangent, and whose equation is not very difficult to find. So, basically we will again have to use the analysis for the direct common tangent that we saw in the previous lecture for the first case. If you remember the first case, so if we remember this slide, so this slide was for finding the slope m of the direct common tangent for case 1, where the two circles were neither intersecting nor were they touching each other. In that case we had got a equation that was quadratic in m, when we said there will be two roots. But in this fourth case, when the distance between the circles is absolute difference between the radius, in that case what will actually happen is that this quadratic equation will only have one root, only one single real root. There will be only one single real root, which basically means that there will be only one direct common tangent, and whose equation can be easily found out. So, the coordinates of this point will be alpha and beta. So, the value of alpha is so this is the value of alpha, and beta will be correspondingly similar. So, alpha will be r1 x2 minus r2 x1 by r1 minus r2, and beta will be r1 y2 minus r2 y1 upon r1 minus r2. And then once we know this coordinates of this point, the equation of this particular direct common tangent will be y minus beta is equal to m into x minus alpha, because we know that this point will lie on the direct common tangent, and the value of m can be will get the value of n from m, will get the value of m by solving this quadratic equation, which will have equal roots. So, both the roots will be real and equal for this case 4, where the two circles are touching each other internally. And of course, in this case there will be no transverse common tangents. So, the number of transverse common tangents will be 0. And then further, as the center of the smaller circle, let us say of this other circle, moves even closer to C1. And of course, the last case is when the center of the second circle moves so close to the center of the first circle along the same line that we had in the earlier cases. So, we were moving the center of the second circle on this line closer and closer to C1. So, we had so this was case 2 when the circles were touching each other, and then this was case 3 when they were intersecting each other, and then we had case 4 when the two circles were touching each other internally. And then if we move the center even further, so then we can have a case something like this, where the C2, the center of the second circle is here, this is the second circle, but then the two centers are so close that C1 C2 is less than the absolute difference between the radii, between the radius. So, in this case, as we can see, the two circles neither intersect, neither do they touch each other, and the second circle is completely inside the first circle. So, this is the fifth case. So, in this fifth case, it is clear that there will be no direct common tangent and there will be no transverse common tangent. So, let us solve some problems to for getting used to finding equations of common tangents. So, in this question we are asked to find the number of common tangents to the circles x square plus y square equal to 4, and the other circle is x square plus y square minus 6x minus 8y equal to 24. So, this first circle, the coordinates of the center is at the origin, radius is 2 units. For the second circle, the center is at 3, 4 and the radius is 7 units. The distance between the two centers is 5 units, and we see that this is equal to modulus of R1 minus R2, which is 5. So, this is precisely case 4 that we were discussing just a few minutes back. So, when the distance between the centers is equal to the absolute difference between the radius. So, this basically means that the two circles are touching each other internally, and therefore, there is only one direct common tangent. There are no transverse common tangents. So, the answer is there is only one direct common tangent. So, let us draw this, try to find out the equation of the direct common tangent. So, this is the coordinate axis, this is the first circle, this is the circle C2 having center C2 and radius R2 equal to 2. The other circle has center C1 and radius 7, which I am just drawing here, but obviously we cannot draw the entire circle because it has a very, this radius is 7 units, and as we can see these two circles touch internally at this point P. So, they have only one direct common tangent. Further, this coordinates of the point of contact, we have already seen the expression. So, using that we will get alpha equal to R1 7 times x2. So, this is x2 y2, this is x1 y1. So, x2 y2 are both of them 0. So, both x2 and y2 are 0. 7 times x2 minus R2 times x1. So, 2 times 3 by R2 minus, sorry, R1 times x2 minus R2 times x1 by R1 minus R2. So, this comes out to be minus 6 by 5, and the y coordinate of this point will be R1 times y2 minus R2 times y1 by R1 minus R2 minus 8 by 5. Now, once we know the coordinates, and we also know that, so let this be the straight line. So, the straight line joining the center C1 and C2, when produced forward, when produced further, will also meet this point P, which is the point of contact of the two circles, and therefore, and further that this tangent will make a 90 degrees with this straight line, and therefore, it is easy to find the slope of this direct common tangent, because this line is at 90 degrees to this line joining C1 and C2. So, this is the C1 C2 line from C1 to C2, and then if you produce it further, it will meet the tangent at this point P. Now, the slope of this line is 4 by 3, because 4 minus 0 divided by 3 minus 0. So, the slope is 4 by 3, and therefore, the slope of this line, because we know that if there are two perpendicular lines, then the product of their slopes is minus 1, and therefore, the slope of this line, which is perpendicular to this C1 C2 line, has to be minus 3 by 4. And then it is very easy to write down the equation, because it will just be y minus beta, which is equal to slope multiplied by x minus alpha. So, the equation is y plus 8 by 5 is equal to minus 3 by 4 times x plus 6 by 5. So, with that we come to an end to this lecture. We will take up some more problems on finding the equation of these common tangents in the next lecture. Thank you.